please.
Thank you very much. Now, before we get started, for those who were on LinkedIn, I don't know if you've seen the post by them, but I think they wanted to be the biggest VMUG in Europe. They wanted to beat the Netherlands. I'm not sure if they succeeded, but what I do know is that they do have the biggest screen in Europe, and maybe even the world for a VMUG, so congratulations on that one. You're at least the biggest in some shape or form. So, when I was talking to the guys, they asked me if I wanted to do a session and host a keynote, and they asked me what I wanted to talk about. So I gave them a couple of options, and some of you may know me from vSAN. That's what I typically talk about. So that is usually what my sessions deal about. So I'm not going to talk about vSAN for the full session today. I'm going to talk about vSAN in some shape or form, but I basically want to talk about innovation at VMware by Broadcom. And I think the by Broadcom is an interesting part here because everything has changed over the last 6 to 12 months for most of us. Now, if you look at VMware itself, and this has been the mission statement that VMware R&D has had for the past 20 years or so. I don't know if anything stands out when you look at this mission statement. Does anyone notice anything when you look at this mission statement? It says, disrupt ourselves so we can disrupt the industry. Is there anything that stands out for you guys? No one? Well, for me, there's one thing that stands out here, and that's that the word customer is missing. It's not explicitly mentioned, and that is one of the things that Hock10 has been driving towards the R&D teams within VMware, that the focus shouldn't be necessarily on ourselves and on trying to disrupt the industry, but trying to help to move our customers move forward, because that is one of the key things, and that's one of the things you're also aiming to do as an IT department or as a consultancy partner, trying to help your customers drive more business. That's what we're all aiming to do here. So as VMware by Broadcom, we're now also aiming to do that going forward. So we're trying to develop solutions which are not only interesting for ourselves from a project perspective, but also interesting for our customers to adopt and use. Now, if you look at innovation, there are 4 different categories where you can categorize the different types of innovations in. And I think it's always interesting to look back, because there's a couple of things that have happened over the last 20 years or so when it comes to innovation. And if you think about VMware, there are a couple of things that I think that stand out. And especially if you look at these 4 types of innovation that we see up on the screen here. Especially the disruptive part and the radical part is something which I think is something that VMware used to excel in. And especially in the early days. If you think about the very first time that you were capable of actually running an x86 machine on top of another x86 machine, that was truly unique. There was no one else in the world that was capable of doing that. And by delivering a solution like that, VMware actually created a completely new industry, a virtualization industry which didn't really exist before then, well, at least not on the x86 platforms. And then, of course, on top of that, when you look at other type of solutions which disrupt an existing market, I think vMotion is probably one of the biggest examples of that. Because when we introduced vMotion, people were capable of doing things on physical platforms, running virtual machines that they weren't capable of doing before. So doing maintenance, for instance, during the day is not something that you normally would be able to do in the physical world, or even in the virtual world without vMotion. So those types of technologies really made a big difference for our customers and for our partners. Now, going forward, of course, if you look at VMware by Broadcom, there are a couple of areas that we are planning on heavily investing in, and we are actually already heavily investing in. And what I'll be doing in this session is actually highlighting 2 specific projects which are still ongoing, and 1 project which I shouldn't say completed, but has already been delivered in some shape or form. Now, going forward, of course, there are a couple of areas which you can imagine will be a focus point. Today there are going to be a couple of sessions talking about machine learning, for instance. Johan is going to talk about machine learning and explain to you what the private AI platform is all about. So I would highly encourage you to visit that session, because that is one of the biggest investments that we've been doing in the past couple of years. But then other than that, for instance, there's also a big push towards these newer types of edge platforms, simply because we see that there's a lot of customer demand from that perspective as well. So we're also highly focusing on that. And of course, security and modern applications have been a focus for the past decade or so, and multi-cloud goes without saying. Now, there are, of course, reasons why we move into a particular space. And this is a slide that I typically use with my vSAN sessions as well, because they because it basically demonstrates the shift that we've seen over the last 10 to 15 years. Now, as technologists, it is something that you tend to skip, because every year or so there are new versions of an Intel CPU popping up, and it's just normal. But if you look at the changes that we've seen to these platforms over the last 15 years, it's actually quite significant. If you look at what the typical data center would look like in 2010, and I'm pretty sure that most of you have actually had or were responsible for a data center that more or less looked like this, you would typically see that in the majority of cases, each host would have 2 sockets. And most of those sockets would have a CPU with anywhere between 4 to 10 cores. That is what the world normally would look like. From a memory perspective, we were typically talking about 128 gigs and maybe 256 gigs at most. And then from a storage perspective, the majority of customers, of course, were using spindles. Now, are people still using spindles for the production workloads at the moment? By show of hands? Says enough, right? Well, there's 2 people in the back. I want to talk to you guys later on. And then from a networking perspective, also a lot, of course, has changed. Back then, people were just about to start moving towards 10 gig networking. But if you look at the world today, and you look at all of the different solutions that have been introduced, and all of the different iterations of CPUs that have been introduced since then, you see that there's a massive shift. If you look at the CPUs, for instance, it's not uncommon to see 64 cores within a single CPU. Now compare that to the 4 to 10 CPU cores that you would have in the past. On top of that, from a memory perspective, we're seeing customers doing 2 terabytes worth of memory or more in a single box. Compare that to the 128 gigs that we had in the past. And then from a networking perspective, of course, there's also a massive shift. We see a lot of customers already moving towards 100 gig networks. So a lot of things have changed. And it's for a good reason as well, because if you look at the workloads, back in 2010, we were deploying virtual machines with 1 to 4 vCPUs. But today, if you deploy a VM, it typically has 4 vCPUs or more. And if you look at something like vSAN, the server itself, well, we know how many vCPUs it has, how much memory it demands, and how many disks it has. And that is just to manage the virtual estate. Now, of course, on top of that, there's also a massive shift from customers moving from just on-prem towards the cloud, whether that's SaaS services, PaaS services, or maybe IaaS services, using something like VMware Cloud on AWS, GCVE, or any of the other solutions out there by Microsoft, etc. Now, those shifts itself also forced VMware to make changes to existing products. And I think one of those examples, for instance, is vSAN. If you look at the solution that we've had over the past decade or so, and when we first developed the vSAN, the original beta release was in 2013, so it was very close to the numbers that we saw in 2010, just on the slide. A lot of customers were adopting vSAN back then, and they were using what we call single-level cell technology from a flash perspective. So this is the storage capacity that they had available. They typically would combine that with some kind of spindles. But today, we have all of these different types of technology that show up in the data center. Now, if you look at the slide here, there's one thing that stands out, in my opinion, and that's the number of times that you could write through a single device itself. Now, if you think about this very briefly, and you think about how we actually designed vSAN back in the day, with just a single flash device sitting in front of a bunch of capacity devices, spindles, right? And that single flash device was typically an SLC device. But now, when I just asked everyone, are people still using spindles? No one raised their hand except for 2 people. That also means that most likely, we're also starting to see all of these newer types of devices within the data center. And that has a direct impact on our solutions that we've developed 15 or 20 years ago as well. Now, you may ask yourself, why is that the case? Well, as I said, if you look at the amount of times that you can write to these devices, that is where the big problem lies. When we initially created vSAN, for instance, the idea was that the majority of customers would be using some kind of hybrid model. Or when they would be using all flash, they would be using SLC at the front end, and then TLC or QLC or whatever, and then end up being at the back end. So the amount of times that they would write would go to what we call a caching disk, and then that would at least be able to cater for those array cycles that would be needed to incur the I/O. Now, as I said, we're starting to see all of these newer types of devices popping up, so that also means, from an architectural perspective, we need to make a change, or we needed to make a change to the platform, and that is something that we've been doing over the last 5 to 6 years. Now, I'm not going to talk in depth about vSAN ESA, but I do want to explain what we introduced and why. And this was primarily driven by hardware changes. And I know when we talk about VMware technology in general, or with the majority of sessions that you will attend today, most people will actually focus on the software aspect of things. And I can understand why, because that's what you actually see in the front end. You look at the vCenter interface, or whatever it ends up being. You look at VROps, or you look at the NSX interface. But from a vSAN perspective, when you look at vSAN ESA, the Express Storage Architecture, which is our new platform, we created this new platform purely because of the changes that we've seen from a hardware perspective. Without those changes from a hardware perspective, there was no real reason for us to actually make changes to the software platform as well. And of course, when we made changes to that platform, when we started thinking about how we could evolve the platform, a couple of things were also added to the requirements list during the discussions that we had with customers. One of those things, for instance, being customers asked us, we like the solution, it's easy to manage, but it would be nice if it would be a bit more efficient in terms of the CPU cycles that it would be using, or if you could do, for instance, more snapshots that we could do now without a performance loss. So that's also something that we've included in the solution that we've built. Now, in this particular case, when we talk about innovation, we had 2 different options to go about solving this problem. The first option would be to completely rewrite vSAN, but we already had all of these different modules in place which worked as they should be working even for a new model. So what we did, instead of actually rewriting the whole stack, is we looked at all of the different components and we actually injected additional components to ensure that we would be able to cater all of the different capabilities that these new flash devices that pop up, TLC devices, QLC devices, would be able to provide us. Now, there's one unique thing about these different types of devices that have been delivered over the last couple of years, and that's that they're all optimized for a specific block size. All of these different devices, so the TLC devices and QLC devices, actually prefer large block sizes. So what we did to actually solve this problem is we injected a different layer within the stack called the log structured file system. And for those who are not aware, log structured file systems have been around for literally over 25, 30 years. Those who are managing Linux systems have probably seen them. And the interesting thing here is that a log structured file system was actually invented by Mendel Rosenblum, who also happened to be the founder of VMware. And we've now implemented the thing that he invented over 25 years ago in vSAN itself to solve the problems that we are facing today. And I think that is probably one of the interesting facts. Now, how we've actually done that, and I think that is probably one of the deeper slides that we'll see today, is that when we implemented a log structured file system, what we actually do from a vSAN perspective is, because with vSAN, of course, we're running virtual machines or we're running container workloads, all of the I/O is going to be random. It could be small blocks, it could be large blocks. We simply don't know what's coming in, but we can identify what is coming in. So we have that mechanism built into the system as well. So as a virtual machine or as a container is doing any type of I/O, vSAN is going to assess what kind of I/O that is, and then based on the type of I/O that we're doing, it's either going to store it in the log structured file system when it's smaller than 128 kilobytes, or it's going to bypass the log structured file system and directly write it to disk, because the devices that it's writing to are already optimized for those larger block sizes. So we have that mechanism built in, so we can leverage those capabilities. Now, the other interesting thing here on the slide as well is it actually mentions a B tree configuration, and those who've done anything with NetApp may recognize that and may understand what it is. But basically what we're doing with the B tree configuration is we're storing metadata about the actual data that you're storing on the capacity devices as well. And the reason we're actually doing that is because that metadata structure allows us to actually create far more snapshots that you would normally be able to create. With the difference being the following. If with VMFS or with vSAN, with OSA, you create a snapshot, what you will typically see happening at the back end is you will see that a new file or a new object is created, and all of the new IOs will go to that new object. Now, of course, this is a pretty decent mechanism, and it works well, but the biggest challenge with it is that if you create multiple newer objects, multiple snapshots, or multiple files, it also means that we need to traverse multiple files or multiple objects in order to read or write data. And there's a delay in that. With vSAN, with vSAN ESA, we've actually solved that problem because we're storing all of that information in metadata now, and we keep writing to the existing object. The big benefit of that, of course, is that when you delete the snapshot itself, we no longer need to collapse all of the different files and objects back into the original object, but we simply can make changes to the metadata structure itself. Now, you may ask yourself, why am I telling you about that? Well, the reason I'm telling you about that is because from an innovation perspective, what we're actually planning going forward is to enable you within the vSphere UI to actually create a snapshot schedule. So I can't tell you which release this is going to be, but it is literally right around the corner. So in the newer release, if you have vSAN ESA, you will be able to specify within vSAN ESA itself what that snapshot schedule should look like. And it's not going to stop after 2 snapshots or after 3 snapshots. You can go 24 snapshots, etc. deep. And you can do that for all of your virtual machines. And the great thing here is that you're actually capable of doing that without performance loss. And that is the biggest difference, or the biggest innovation within vSAN, from my perspective, that is relevant to customers. Because ESA versus OSA may not bring you any additional capabilities other than some performance gains. But being able to create 24 snapshots and being able to protect against certain failures is something that could be very valuable to the business. Now, there is another shift happening at the same time, and those who actually paid attention when I showed the 2010 and now slide, it also mentioned DPUs and GPUs on there. And I know there's going to be a couple of sessions later today talking about AI, so I'm not going to talk about GPUs, but there's also something happening in the networking space, and that's the DPU. And I know people actually look into this, sometimes it's also being referred to as a smart NIC, but basically what this solution allows you to do is to create a platform through which you can drive more traffic. And I think this, for some of our customers, is extremely crucial. When we were having conversations with our customers about some of the bottlenecks that they were having in data centers, a couple of things started popping up. We had some customers that simply weren't capable of driving traffic fast enough to run the workloads that they wanted to run. So they were running extremely large in-memory databases, and the amount of traffic that had to go across the wire, they couldn't physically push through their CPUs that they had within their system. So the amount of CPU cycles that the system was using simply to do networking barely allowed them to run any virtual machine on the platform itself. So you can imagine that imposes a whole bunch of challenges. So after having those conversations with customers, and seeing what was happening in the industry, we figured that we could potentially do something with that technology that popped up. Because if you look at the technology itself, and I don't know if people actually looked actively into DPUs, have people looked into DPUs by show of hands? Just a few people. So for those who don't know, if you look at this device, it looks like a networking card, but the big thing here is that if you look at all of the individual components, it's not just a networking card, but it's, in my opinion, a small server, because it actually contains all of the components that a server has as well. It has a CPU, it has networking, it has a memory capacity, it has some form of storage. All of those different components are included in this platform. And the nice thing about this platform itself is that it's a programmable platform on top of that. So we as VMware can actually program this device to offload certain capabilities. Now, you can imagine that if you're running a solution like, for instance, NSX, that this could be one of those devices from which you can greatly benefit if you can offload some of those NSX capabilities, whether that's firewalling or routing, to that device. So instead of your x86 CPU handling those capabilities, these devices, these DPU devices, which are available through different vendors, can also handle these capabilities. Now, before people get overly excited, I do want to point out one thing. I'm Dutch, so I'm always open and honest about these things. There is no HA or availability mechanism just yet for these devices. So when you run a device like this, at the moment, we're working towards that. But if you run a device like this, it's a single device that runs, which also means there's some kind of single point of failure. I'm just being open and honest here so people understand what some of the challenges are you have with this platform still at the moment. But of course, we're hoping to solve these problems. Now, when you look at this platform itself, you may ask yourself, okay, if I offload it, are there any changes that I can expect from a performance perspective or maybe from a capacity perspective on my host? And of course, we did those tests as well. And those changes are actually significant because if you look at these numbers, and these numbers were done with a firewalling solution, and we did these actually for a customer because they were running into a situation where the amount of CPU capacity, like I said, that a single host was consuming simply to run the firewall didn't allow them to run any additional virtual machines next to the firewall on that host anymore. So they wanted to offload that mechanism. So by offloading that mechanism, and especially if you look at the top one, and you look at the amount of bandwidth that a single DPU can drive compared to what the host itself could drive with running the exact same software, it's about 4.5 times more. Now, the interesting thing here is that if you look at the amount of CPU consumed on the server itself, so your x86 platform, it's almost, or it's very close to zero compared to 12 cores, which you would normally be using on that server. So you can imagine if you open up those 12 cores for your virtual machines, you can now actually run the workloads that you need to run on that platform as well. And then on top of that, if you look at the amount of data being processed, right, there's a big difference between 4 or 5% compared to almost 100%. So that is the big difference, or that is the interesting thing about this platform that we are working towards. Now, of course, that's not where it stops, because that's what we have available today. You can imagine that in the future, we'll be able to use these type of devices to offload other services as well. Now, for those who are already using vSAN, are people doing anything with HCI mesh by show of hands? Anyone connecting? There's, of course, Hans is doing HCI mesh. HCI mesh, for those who don't know, basically allows you from a vSAN perspective to connect vSAN clusters to each other and share the data store wherever needed, but you can also connect non-vSAN clusters to vSAN clusters itself, even across vSAN to servers. So if you have sufficient capacity in one cluster and you don't have sufficient capacity in the other cluster, you can simply connect them. Now, when we make that connection, of course, we use the x86 platform to make the connection. But what we're actually planning on doing is allowing you to make that connection potentially in the future as well across a DPU. So we can use that data processing unit, that SmartNIC, to connect vSAN to other platforms in the future as well. That is one of the things that we're working towards from a DPU perspective. The other thing, of course, that we're considering from a DPU perspective is to see if we can connect physical machines directly to the vSphere estate as well for various services. That could, for instance, be something like security services that NSX provides. So you have your physical Windows machine with a DPU. The DPU is running NSX, and it's still providing those networking services and those security services for that physical platform. On top of that, for a solution which is not directly managed by VMware. So this is a physical machine running Windows or Linux. That is also something that we are now working towards. Now, if you look at what stands out from the slides that I've seen or shown so far, is that it mainly deals about data. And I think when we talk to customers about data, this is typically where the challenge is as well. And of course, I'm a vSAN guy, so we like to talk about data and data capacity, but that's not what data is all about. Because at some point in time, typically before you store the data on disk, it also needs to be stored on memory. And that is probably where the biggest shift is going to be in the upcoming years. When we talk to customers, and we talk to customers about some of the challenges that they are facing, and I think those are going to be apparent in the sessions later on as well, one of the things is that they're seeing an explosive growth of data. Now, the explosive growth of data is typically not a huge challenge because the majority of people actually have sufficient storage capacity to store that data. The bigger challenge for majority of customers is going to be somehow to be able to load that data into memory. Because if, at least from my experience when I talk to customers, if they are challenged, they're not challenged from a CPU perspective, they're typically challenged from a memory perspective. And that is going to be worse, especially with those AI and ML workloads where we have larger data sets that potentially need to be loaded into memory, and some of that may need to be processed real time as well. So VMware has seen those changes in the industry happening and started thinking about what we could do to solve the memory problem. And it's not an easy problem to solve. Because if you look at the memory problem that is out there today, there are a couple of things that stand out. And I don't know if people have actually thought about this, but when you configure a server itself, the first thing people tend to do is they pick a CPU. And then the next thing they tend to do is they select the amount of memory that they would like to have for that host. And then typically what happens in some cases is you may go to the website that Frank Denneman owns and you look at the amount of memory modules that you need to have for NUMA to be optimized for that particular CPU. And if you don't do that, you may end up in a situation where you have some kind of performance degradation. Because that is the biggest challenge that customers have today, is the amount of memory modules that you can have within a single host while still maintaining the exact same performance. Not only from a performance perspective there's a challenge, but there's also a challenge from a capacity standpoint. If you look at CPUs and you look at the amount of CPU capacity available, from 2010 to now 2024, we've seen the amount of cores double almost every year, and also this amount of CPU cycles, at least from 2010 to 2015, increased significantly. And we're still seeing the number of cores going up. But from a memory perspective, we haven't seen that, unfortunately. Of course, there are larger DIMMs, but they're fairly expensive. So there are challenges here. And you may ask yourself, well, why do we see those challenges? Well, it's fairly simple. It's physics. If you look at the CPU itself, it has an X number of pins on the CPU itself. And it's simply limited by the width of the pin itself. They can't get any smaller, so we can't create additional pins on that particular CPU, which also means that the amount of memory lanes that we can have towards that CPU is also limited. So there are a couple of challenges here from a memory perspective when you look at the host itself, which are fairly difficult to solve from a physics perspective. So if we can't solve them with physics, potentially we can solve them within software. And that is something that we're actually looking towards solving. And the reason we're planning on doing that is because we're actually starting to see real problems in customer environments as we speak today. As you know, VMware collects data from customers as well if you opt in. And if we look at the data set, what we're actually starting to see is that the majority of our customers are actually over-provisioned from a CPU perspective compared to memory. And what we're aiming for, hopefully in the future, is to see a bit more balance between CPU and memory so that they can actually use the full capacity of their hosts that they have available instead of only using 30 or 40% of the CPU capacity while they're actually full from a memory perspective. So the way we potentially can go about doing that is by introducing additional tier of memory. Now, I don't know if people have seen or heard about this, but we're actually working towards a solution where we can tier memory. Now, the reason we're actually planning on tiering memory is simply because we cannot add additional DIMMs within that platform. Now, when you look at all of the different types of devices available, and you look at this pyramid, you'll see that the way that it typically works from a tiering perspective is that with DRAM being on top, which is extremely expensive but extremely fast, the lower you will go, you will see that it becomes a lot cheaper, but it also becomes a lot slower. So if we introduce a tiering mechanism, we need to make sure that from a tiering perspective, this solution actually not only provides capacity, but of course, on top of that, also provides performance. And that is something that we're planning for in the near future. What we actually actively working on today is a memory tiering solution which enables customers to provide both DRAM as well as flash capacity, so NVMe-based flash capacity, to their virtual machines as if it is memory. So from a logical perspective, if you look at it on the left side, the virtual machine will see just DRAM. From a physical perspective, the virtual machine may have DRAM and potentially pages stored on flash devices as well. So we have that, or we're now actively working on that and hopefully be able to deliver that in the near future. Now that introduces a couple of interesting things, of course, because when you store memory pages on flash, the access time is probably going to be at least 100x slower. So we need to think about what we store on that slower tier before we actually move it. And as you can imagine, we have all of those capabilities built into the platform already, because the hypervisor already manages all of the different memory pages and knows what's being stored where, and it also knows how many times it's being read and how many times it's being written to. So we have that capability within the platform. We're simply already monitoring the memory pages. So you can imagine that when you monitor the memory pages at the moment, we can also make smart decisions in terms of where we store those memory pages. If they're not being frequently accessed, we may as well move them to a slower tier. On top of that, because we have capabilities like, for instance, DRS, we can also move those virtual machines, which are very active from a memory perspective, to potentially a host which has more DRAM available, to make sure that we can actually cater for the performance requirements that that particular virtual machine has. So that is something that we're now working towards from a platform perspective. Now, of course, you may then ask yourself, what does that result in? Because when you move those pages around, that of course is going to be an impact. Even if they're not frequently accessed, being read or written to, there's going to be some kind of performance impact. If you would do that without any form of smart tiering, the performance impact would be quite significant. If you look at this particular graph, and the first line that we're now seeing is without any form of tiering, you can see that the first dot is 32 gigs worth of DRAM, 0 gigs worth of flash capacity, but the second one is 50% DRAM and 50% flash capacity, and it immediately has a 23% performance impact, which is quite significant. And of course, it keeps going down as the amount of DRAM goes down as well. When we inject the modules that we've created into the hypervisor itself, and it actually manages what is being stored where, and that is the second line that we're now seeing, you can clearly see that the impact on the workload itself is not as significant as it is without the smart tiering platform. So we're just talking about the first step, we're talking about a 6% performance loss instead of a 23% performance loss. Now, of course, this sounds great, but I didn't trust what the developers told me, so what I wanted to do is I wanted to make sure that that is actually what is happening in real life as well. So I spoke with one of the developers and I asked him to actually create a demo, and that is what he ended up doing. So what we're actually seeing up on the screen right now is HammerDB, and where we see the large number, 1.5 million transactions per minute. This is our benchmark or our baseline virtual machine, which is only using DRAM at the moment. The second screen next to it, where we're actually seeing 1.3 million transactions per minute, is where we are actually using 50%, close to 50% NVMe capacity, 50% DRAM capacity. And as you can see in the graph itself, it currently is reaching about 82% compared to the baseline itself, but that will fluctuate, of course, depending on the pages that we're reading from or writing from. As soon as the workload stabilizes, you will see that it's basically going to be a flat line hovering around 90%. So this is the big benefit that we have. Now, reminding you that 50% capacity that we're using here is actually coming from NVMe, and these devices are probably 100x slower, if not more, than the memory capacity that we have in that host. Now, of course, there's a big benefit that comes with this, because the cost of those flash devices is probably also 10-15x lower per gig than those memory modules would be if you could even expand within that host, if you would have empty DIMM slots. So that is the big benefit of this platform that we're presenting here. Now, that was just NVMe capacity, but there's more happening within the industry right now. And I don't know if people have seen this. I spoke with Johan about this yesterday, about CXL modules. And CXL let me show what the device actually looks like, is a new type of device which you will see popping up in data centers probably in the upcoming years. It's already available right now, but I don't expect anyone in the room to actually have deployed this. Is anyone using a CXL device at the moment? No, that's what I expect. I've never seen anyone raise his hand in any of the sessions I've done so far. But these types of devices are actually devices which can be connected over PCIe, and CXL is the protocol that's going to be used to access the memory within these devices. It's an interesting thing here because we're actually catering up memory through PCIe through a new protocol, CXL. And this CXL protocol was specifically written to be able to access memory over PCIe. Now, of course, from a performance perspective, there's still going to be a difference. Some of you may think, okay, it's connected to PCIe, so it's going to be similar to DRAM. No, it's not going to be similar to DRAM because that PCIe bus actually has a limitation as well in terms of throughput and bandwidth. It's not the same as a memory lane. But still, it's fairly close, and at least it's much better than an NVMe device because this device is actually optimized for memory access. So you can imagine that if we are capable in the near future of actually doing performing some kind of memory action on NVMe, that we will also be able to do that in a more distant future as well on CXL devices. So that is also something that we're planning for. So expect this to show up in data centers for those doing large memory configurations, probably in the upcoming 3 to 4 years. Now the reason, of course, we as VMware by Broadcom are investing in that is because this market is expanding extremely rapidly. As you can see, 2022, fairly small market, 1.7 million, but the expectation is that there's going to be a 15 billion market in 2028. And that says something about how fast this technology is going to expand. So it may not be available where you work today, it will probably be available within 2 years. Now, the other thing that then leads us to is other opportunities for exposing memory to workloads. And this is one of those questions that I would get 20 years ago when we started doing virtualization as well. Oh, if I can run my virtual machine on one host, can I access the CPU or memory on the other host? And of course, the answer was always no, that's not going to be possible. Where you run your virtual machine, that's where you access the memory, and that's where you access the CPU. Storage can be anywhere, but memory and CPU needs to be local. However, with the technologies that we're now developing, with CXL, and potentially CXL over RDMA or over Ethernet, we could actually start pooling memory across clusters as well. So you may have multiple hosts within a cluster, let's say 6 hosts, some of which are running out of memory, some of which may have sufficient memory. And we could potentially actually start leveraging memory capacity in other hosts without actually moving the virtual machine from one host to another host, simply by leveraging that CXL protocol which has already been developed. Now, when I talk about this is, to be clear, this is not, of course, going to be something that's going to be available next year before anyone asks at the end of the session. This is going to take a while. But this is something that is realistic and something that we're already working towards. So you can expect capabilities like these to be available at some point in the future. Now, of course, not just for DRAM, but potentially also for NVMe, maybe for large boxes of DRAM, maybe for large boxes with CXL capacity, but potentially also for FPGA type of devices. Now, when we talk about these FPGA type of devices, one of the things that we as VMware by Broadcom are also working towards is developing our own device. Now, I can hear some of you thinking, and I know Johan asked me the question yesterday as well. He says, okay, that's cool. Clearly, because you're working with Broadcom, you're now developing a device with Broadcom as well. And just to be open, this device is not created in conjunction with Broadcom. This is done with a different vendor. It may happen with Broadcom in the future, and I can see it happening with Broadcom in the future. But as it stands right now, we're working with another vendor to actually develop a device which allows us to start sharing memory and start accessing memory in a different way as well. And that's what we're using this FPGA device for, which is called Project Peaberry. And if you'll Google it, you'll find a couple of papers on Project Peaberry out there as well. So what is Project Peaberry about, and why are we doing this? Well, simply said, when I spoke about DPU about 15 to 20 minutes ago, one of the big things about DPU was offloading mechanisms that were running within the hypervisor itself, like NSX or potentially vSAN, to that DPU device to ensure that we could use the x86 CPU cycles that we had for virtual machines. That is very similar to what we're planning on doing with Project Peaberry. Because if we're actually using the hypervisor and the x86 cycles to start moving memory pages around, there's going to be a cost associated with it. And you can imagine that if we have a device available which we can program ourselves, which can keep track of where memory pages are being stored and how frequently they are being accessed and where they need to move to, that also means that the load on the host itself will go down. And that's where we can actually start using this device for. The other thing, of course, that we can do with this device is we can start connecting hosts within different ways within the cluster as well. So you can imagine that if you would have this Peaberry accelerator, as we call it, within multiple hosts, we can now actually start interconnecting those hosts, and actually have CXL connections within those hosts, and being allowed to actually start sharing memory across those hosts as well, as if it is local. So the way I go about looking at these types of devices is that it's a abstraction layer for memory. So basically what VMware did for CPU cycles through the x86 platform, it's now planning on doing for memory through this Project Peaberry device as well in the future. And that will hopefully allow us to actually start creating these configurations which are not only optimized from a performance perspective, but probably for a lot of you also, maybe even more importantly, optimized from a cost perspective as well, which will allow you to start running these larger memory workloads on platforms which normally would not be able to run these types of platform or type of solutions. And like I said, hopefully it will solve some of those problems. And when we spoke to customers, those problems again were very clear. Lower the amount or lower the cost for memory within those types of devices, but more importantly, allow us to run these types of workloads which we're not capable of running. And I know Johan is going to talk about one of those types of workloads, which is going to be AI, which are extremely memory dependent. And these solutions like these will be able to cater to run those types of solutions on top of that platform. Now, hopefully, within the last 45 minutes or so, I've been able to show you what it is that we've been working on for the last 18 to 24 months, but also for the last 5 years with vSAN ESA. Now, just to be clear, as I said initially, when I mentioned the mission statement, the word customers was not mentioned in that mission statement, but going forward, that is going to change, and that's already changing within VMware. There is a very clear mandate as it stands right now to ensure that everything that we're actively working on is also something that is of interest of you. So before I'll let you guys go, there's one ask I have you. We've seen 3 different projects presented here. The first was vSAN ESA with scalable snapshots. The second was the DPU technology that I spoke about. And then the third was memory tiering. What I would like to get from you is some kind of feedback on those projects, if they are useful, or if they are not useful. And that may not be culturally appropriate. I know for most Belgians, they're not as blunt as us Dutch people, but it's okay to tell us that our baby is ugly. And with that, I would like to thank you for attending my session, and hopefully you'll have a great rest of the event. Thanks.